Myself, Sarnasundram, Professor, Sri Ramakrishna Engineering College, Coimbatore. This video is about coupled circuits, and in this video, problems related to coupled circuits are discussed. This video covers problems on equivalent inductance of series and parallel coupled circuits, application of mesh analysis for solving coupled circuits, then self-inductance and mutual inductance. So this is a continuation of coupled circuits part 1. In coupled circuits part 1, the basics of coupled circuits are discussed. Concepts of self-inductance, mutual inductance, coefficient of coupling, then series and parallel coupled circuits, and writing equation for coupled circuits are discussed. Let us consider this example. Two identical coupled coils in series has an equivalent inductance values of 0.084 Henry when aiding and 0.0354 Henry when opposing. Find the values of L1, L2, M and K. So L1 is self-inductance of coil 1, L2 is self-inductance of coil 2, M is mutual inductance, K is coefficient of coupling. I think you have understood this problems. Two coils, coupled coils, they are connected in series. You are asked to find the inductance values of each coil and their mutual inductance and coefficient of coupling. So aiding connection, the value is given as 0.084 Henry. That is L1 plus L2 plus 2M. This value is given as 0.084 Henry. And whereas opposing connection, L1 plus L2 minus 2M. So this is given as 0.035. So now equate this to 0.084 and this to 0.035. And this is the general equation for equivalent inductance of coupled coils connected in series. Now you subtract the second equation from first equation. So you get M is equal to 0.0545 divided by 4, which will be equal to 0.01125 Henries. And it is given in the problem that two coils are identical, therefore L1 will be equal to L2. If we substitute M in any one of the equations, you can find L1 plus L2. Since two coils are identical, L1 will be equal to L2. So therefore this value will be equal to half of this value, L1 plus L2. So divide this L1 plus L2 by 2. So you will get 0.02875 Henries. Then to find the coefficient of coupling, so we know that M is equal to K into under root of L1 into L2. So from this equation we get K is equal to M by under root of L1 into L2. So under root of L1 into L2, just I'm going to call it as L, which will be equal to this value. So M by L will be equal to 0.392. Doesn't have any unit. This is how you should solve this problem. Coming to the next problem, let us see how to write KVL equations if a coupled circuit is given. Let us consider this circuit. There are two meshes. The first mesh, we have voltage source, resistance and inductor L1. Its reactance is given as J omega L1 and R2. In the second mesh, again we have this resistance J omega L2 and R3. So here they are coupled and the dots are shown in the coils, and here this is the dot for this coil and this is the dot for this coil. And M is the mutual inductance between the two coils. So now while writing equations, you're going to apply Kirchhoff's voltage law for each mesh. So for that you have to assume the current direction. So clockwise directions are assumed. They are named as I1 and I2. So general equation for this mesh will be Z11 into I1 minus Z12 into I2 minus Zm into I2 equal to Vs, particularly for this example. Let us see what is Z11. Z11 is nothing but sum of all the resistance and reactance in this. So R1 plus R2 is the resistance and reactance is J omega L1. So you have to write here R1 plus R2 plus J omega L1 into I1. Then this term has positive sign. The second term is Z12. That is the impedance that is common between mesh 1 and mesh 2. So this is the element R2. This is the resistance that is common between first mesh and second mesh. Therefore, Z12 equal to R2. Here we have a minus sign. This is incorrect. So why we are writing minus sign here? You compare the current directions. If these currents are flowing in the opposite direction through this resistance, then you have to write here negative. Otherwise, you have to write here as positive. For example, in this case, I1 is flowing from top to bottom, whereas I2 is flowing from bottom to top. So they are opposite. So you have to write here minus sign. Then the last term, in normal mesh analysis of AC circuits, we will stop here. In coupled circuits, you have to consider voltage drop in the mutual inductance also. Suppose since only one coil is present, so there will be one voltage drop due to mutual inductance. Let us see how to write. So the mutual inductance is M. Its reactance will be J omega M. So multiply with this with J omega M. Then into this coil is coupled to which coil? To this coil. And what is the current that is flowing in this coil? It is IT. So therefore this current you have to multiply with this. That is J omega M is the reactance multiplied by this is because of the current flowing in the neighboring coil, that is coupled coil, that is I2. So this will be equal to Vs. So normally you used to write minus Vs equal to 0. If you write it in the right hand side, you can write straight away as Vs. Coming to the second mesh, the general form of writing is minus Z21 into I1 plus Z22 into I2 minus Zm into I1 equal to 0. Let us see one by one. Z21 is nothing but the impedance that is common between second mesh and first mesh. Again, this is R2. So R2 into I1, that's right. And the sign depends on the current direction. So already we have seen that I1 and I2, they are flowing in the opposite directions in this resistance. Therefore, you have to write minus. Then plus Z22, you have to write plus. Sum of all the resistances and reactances in this, that's R2 plus R3 plus J omega L2, you have to write it here into I2. Then coming to there is a coil. It's a right here. This coil is coupled to this coil. Therefore, it has got mutual inductance M. Therefore, there will be drop in the mutual inductance M due to the current flowing in the neighboring coil. So, therefore, this will be equal to J omega M is the reactance. What is the coil coupled to this coil? And what is the current flowing in this is I1. So, therefore, you have to multiply I1 with that reactance. J omega M into I1 equal to 0. So there is no voltage source, so you have to write it as 0. So this is how you have to write the equations. Now, if you know the values of R1, J omega L1, then you can solve these two equations by Cramer's rule and you can find the mesh currents I1 and I2. So same thing is explained here. So the same circuit applying KVL to mesh 1 we get. So this is the general equation Z1 into I1 minus Z1 into I2 minus Zm into I2. So here this current, right, while we are writing for this mesh, this current is nothing but right. So this coil is coupled to this coil. The current in the coupled coil, that is this one, I1, because of I2 only, this voltage drop due to mutual inductance occurs in this first mesh. So that you have to write here. Again, the same thing is written here. Vs is written the right hand side, and again here I2 terms are combined. So Z11 is nothing but sum of all the resistances and reactances in this first mesh. What is Z12? Z1 is sum of the resistance and reactance of self inductance common between mesh 1 and mesh 2. That is this part. Suppose there are two elements in series, you have to add them. The negative sign indicates that the assumed mesh currents, that is I1, I2, they are flowing in the opposite direction through Z12. And this term minus Z term is nothing but the reactance of this mutual inductance. It is J omega M. And here the negative sign indicates that, see here when we write negative sign, it means that the current is entering into one dotted terminal and current is leaving in another dotted terminal in the coil. There are two coils. For example, you see here, I1 is entering the dotted terminal. Whereas what about I2? I2 is leaving the dotted terminal. So therefore, if one current is entering into the dotted terminal of one coil and that in another case, if the current is coming out from the dotted terminal in another coil, then you have to write here minus sign. So here current I2 is the current that produces voltage across mutual inductance and it is flowing in the coupled coil L2, that is neighboring coil. So here Z1 is nothing but R1 plus R2 plus J omega L1 and minus Z12 is nothing but the common element minus R2. Now straight away we will go to the problem. So calculate the mesh currents in the circuit shown in figure below. So this is the circuit. So here 100 volts, 4 ohms, minus 3 ohm, J 8 ohms, J 2 ohms. This is the mutual inductance reactance, the reactance of the mutual inductance. J 6 ohms and 5 ohms. So the current directions are marked here. So if current directions are not given, you have to assign the current direction. Now only you can assume the current directions as clockwise direction. So these two coils are coupled coils. So the dots are placed here. Now let us see how to write the equation. Okay, with I1. So Z11 is nothing but we have to sum up all the resistance and reactances in this. So resistance is 4. Net reactance is minus J3 plus J6 is plus J2 into I1. Then coming to Z12 is the element that is common between first mesh second mesh, which is minus J6 into I2. Then the last term is for mutual inductance. So here these two coils are coupled. So therefore the mutual inductance is J2. So J2 into which current you have to multiply. So this coil is coupled to this coil. What is the current flowing in this? It is I2. So J2 into I2 is the voltage drop. So then you have to find out this sign. The sign, if you see here current I1 is entering into the dotted terminal in this first coil. What about the second coil? Current I2 is leaving from the dotted terminal. So in one coil it is entering, in another coil it is leaving. But right here minus. And this equated to the voltage source 100. Suppose this is the polarity, you have to write here plus 100. If the polarity is reversed, here minus, here plus, you have to write minus 100. So this is first equation. So coming to the second loop, again Z21, that is, so this is the element common between the two meshes, therefore you have to write J6 into I1. So the sign depends on the current directions in the coil. So I1, I2 they are the opposite directions. So therefore you have to write here as minus 6 I1. Then plus Z22, you have to sum up all the resistance and reactance in this. That is J8 plus J6 is J14. 5 plus J14 into I2. Okay. Then the other terms are mutual inductance. There are two coils, therefore, so you have to write voltage drop due to mutual inductance of this and due to mutual inductance of this. So coming to this coil, for this coil, both coils the mutual inductance J2. So while writing for this coil, J2 into, you have to consider the current in the coupled coil. Current in the coupled coil is I2. So J2 into I2 you have to write here. So now let us see the sign. So while considering this coil, the voltage drop in the mutual inductance will be J2 into what is the current in this coil? It is I2. Now you have to determine the polarity. Now you are writing equation for the second mesh. So in the second mesh, the current I2 is considered to be positive. So this I2 current, if you see, it is coming out from the dotted terminal, and here also it is coming out from the dotted terminal. Therefore, you have to write plus sign here. So while you write the equation for current for this, it will be I2 minus I1 while you are writing equation for second mesh. I2 is considered as positive current. Next, while writing the voltage drop due to mutual inductance for this coil, again it will be the mutual inductance reactance. It will be J2, and what is the current flowing in this? It is I2 minus I1. So J2 into I2 minus I1. What about the polarity? Already I told you that since we are writing equation for this mesh, here you have to consider I2. I2 is leaving from this terminal, also it is leaving, so write plus here. So you got two coils, you got two equations. So now you write this equation in terms of I1, I2. Then put these two equations 1 and 2 in the matrix form. Then solve for I1, I2 using Cramer's rule. That is determinant method. So you find delta. Delta is nothing but the determinant of this matrix. Then find out del 1. Del 1 is nothing but remove these two elements and replace with these two elements. So find out the determinant of that matrix. That will be this. So find out del 1. Del 2 is again in this matrix. So this second column element should be replaced with 100 at an angle 0. So you will get del 2. Now find I1 as del 1 by del. So you'll get 20.3 at an angle 3.5 degrees. I2 is del 2 by del, which will be equal to 8.7 at an angle 19 degrees. So this is how we should solve this problem. Next, determine the voltage V0 in the circuit shown in figure below. So this is the circuit given here. These two are coupled coils, and the reactance of the mutual inductance is given as J2 volts. And you are asked to find the polarity across this. So now what you do, as usual, find out I1, I2. Then for the given polarity, the voltage across this will be equal to, so that is I1 minus I2 into J6 plus the drop in the mutual inductance for this inductance. So that drop will be J2 into I1. So this is caused by the current in the neighboring coil, J2 into I1. So what about the sign? You have to decide. So here current is entering here, the dotted terminal, and here it is leaving. So therefore you have to write minus sign. Now let us write the equations. Again, Z11 is, so add the resistances and reactances in this mesh, 5 plus J9 into I1. Then Z12 is nothing but the common impedance between the two meshes. It is J6 into I2. The minus sign is written here because these two currents are flowing in the opposite direction. So one flows top to bottom and another flows bottom to top. Then the mutual inductance equations. So here, first let us write for this. So the mutual inductance J2 into, so the current you have to write this, for with this you have to multiply by the current that is flowing in the neighboring coil. That is, in this coil the current is I1 minus I2, but you are writing for mesh 1. So J2 into I1 minus I2. So then you find out the signs. That this I1 is entering into the dotted terminal, whereas here I1 is leaving from the dotted terminal. So in one terminal it's entering, in another terminal it is leaving. Therefore you have to write here minus J2 into I1 minus I2. And coming to this coil, for this coil the voltage across the mutual inductance will be again J2 into, so the current in the neighboring coil it is I1. So the polarity you have to write, since already we are seeing that the current I1 is entering here in the dotted terminal and here it is leaving, therefore we have to write minus 1. So this is equal to 10 volts. Now you separate I1 and I2 terms and you get this equation. Similarly for second mesh, we'll write the equation. So Z21 is nothing but the drop uh, in the branch which is common between second mesh and first mesh. So that is J6 into I1. So the minus sign because these two currents are flowing in the opposite direction through this. Then coming to Z22, you have to add the impedance and reactances in the second mesh. That is minus J4 plus J6 is J2 into I2. Then the mutual inductance term. So since one coil is present, so there will be mutual inductance drop. So that mutual inductance reactance is J2 into current in the neighboring coil is I1. So right here J2 into I1. So what about the current directions? While writing equation for second mesh, this current I2 is entering here. Whereas in this I1 is entering the dot. So in both cases, the currents are entering. So right here plus. Now separate I1 terms, I2 terms. So you will get this equation as like this, equating to 0. Now put these equations in matrix form. Then find I1, I2 using Cramer's rule, like we did earlier. So now you write the equation for V0. It is minus, that is, it is J6 into I1 minus I2. Why I am writing I1 minus I2? Because for this given polarity, you get this polarity only when current I1 is of this polarity. But if so, therefore we can keep this current as positive. So I1 minus I2 because I2 is now opposite to I1. If it is the same direction, you have to add. Since it's the opposite direction, you write I1 minus I2 into the impedance of this. Then with this, you drop in the mutual inductance. That is minus J into 2I1. So minus J2 into current in the neighboring coil is I1. So the minus sign because here current I1 is entering here where it is leaving here. So now what you do is substitute the I1 and I2 in these equations. So you get V0 as 7.04 minus J 11.76 volts. Next, coming to the next example, find the phasor currents I1 and I2 in the circuit below. So here these two are coupled coils. The reactance of mutual inductance is given as J3 ohms. And here in this first mesh we have voltage source 12 at an angle 0, capacitive reactance minus J4 and inductive reactance J5 ohms. Here this side we have inductive reactance J6 ohms and resistance. problems. The current directions are assumed clockwise and I1, I2. So now KVL equation for the first mesh it gives. So here you can write these equations. Minus 12, right? If you are writing in the left hand side directly, you can write for this polarity. The current is coming out from the positive term, you can write minus 12. Then plus the I1 term, Z11 is nothing but add the resistance and reactance in this. That is minus J4 plus J5 into I1. Okay, then the mutual inductance voltage. For this coil, the mutual inductance is J3, K3 into, so which is causing this voltage drop. That is the current in the neighboring coil. That is current which flowing in this is I2. So J3 into I2 you are 5. So then we find out the polarity. Here I1 is entering the dotted terminal. Here I2 is leaving the dotted terminal. So therefore, so in one terminal it's entering, another terminal it's leaving. Right here minus. So separate I1, I2 terms, you will get this equation. Coil 2, the KVL equation is, so this part with I2, you have to add the resistances, reactance in this part, that is 12 J6. So with this, you add the voltage drop in the mutual reactance. So here the mutual reactance is J3 into, which is causing this voltage drop, the current in the neighboring coil, that is why. So J3 into I1 is the voltage drop in the mutual inductance. So here sign polarity, here it is written as minus because the I1 here it is entering the dotted terminal, here I2 is leaving the dotted. So here it is plus minus. So now you solve these two equations. Either by Cramer's rule you can solve it. So you got two equations in terms of I1 and I2. So these are the two equations. So otherwise by subtraction method you find out the currents I1 and I2. So the current I1 and I2 you find out, and these are the values. I2 is 2.91 at an angle 14.04 ampere. I1 is 13.01 at an angle minus 49.39 ampere. Next problem. Find the phasor current in the network shown in figure below. Find also the power supplied by each source. So here they are asked to find phasor currents I1, I2 and also the power supplied by the source. So now what you do is, if you want to find out the power supplied by the source, you have to multiply current with voltage. You also multiply this current with this voltage because I2 is the current that will be supplied by the source and here I1 is the current supplied by the source. Multiply and the real part gives us power. The mesh equations are for this mesh, it is 120 plus J0. The voltage itself you can write as equal to sum of the voltage drops. That is, you add in this case the resistance and reactance in this part of the circuit. So in this mesh, that is 4 plus 8 J8 into I1. Then you may not see the common element between the two circuits because these two are only coupled circuits. So here only you write the mutual inductance voltage drop here. So that is mutual inductance voltage drop is J4 is the mutual reactance, and here into, for this coil you have to consider current in this coil, it is I2. So now you see this sign, since I1 is entering the dotted terminal, I2 also entering, so you have to write here plus. This is the equation for this part of the circuit. So this voltage, that is 120 at an angle, can be written as 0 plus J120. This is the voltage source. This is equal to, so here here sum up this resistance and reactance 4 plus J4 into I2, that will be the drop here, and plus this voltage drop in the mutual inductance. So that is mutual inductance, this coil is coupled to this, therefore J4 is the that is reactance of mutual inductance. This multiply by I1, it will be the voltage drop across this mutual inductance, and sign is positive because both currents are entering the dotted terminal. Now using Cramer's rule, right, put these equations in the matrix form, find I1 del 1 by del, and then simply find I2 del 2 by del. So you'll get J20 here, and here you'll get 10 minus J20 ampere. Now power delivered by the sources. What you do is, so now if you see this circuit, the current supplied by the source is nothing but I1, and for this source it is I2. So multiply this voltage with the current I1. Now if you multiply, you will get real part and imaginary, but the real part gives us power, that is 1200 watts. Similarly, to find out power delivered by the another source, so again you multiply this part, J120 is the voltage, multiply by minus J20 is the current. So the real part of this will be 2400 power supplied by the source. Next example. So when one coil of the magnetic coupled pair has a current of 5 ampere, resulting fluxes Φ11 and Φ12 are 0.2 milliweber and 0.4 milliweber respectively. If the turns are N1 equal to 500, N2 equal to 1500, find L1, L2, M and coefficient of coupling K. So I think you have understood this problem. There are two coupled coils. In one coil, current 5 ampere is flowing. Because of this current, the fluxes Φ11 and Φ12 are produced. Φ1 is nothing but the flux linking only with that coil. Φ12 is nothing but the flux that is only linking with the neighboring coil, coil 2. They are given. The turns of coil 1 and coil 2 are given, and you are asked to find out this. Solution is first to find out the total flux in the first coil. So first coil will be Φ11 plus Φ12, which will be equal to 0.6 milliweber. So you add this 0.2 plus 0.4. Now let us find the inductance L1. L1 is nothing but, you know the formula, N1 into Φ1 by I1 is the formula. The N1 into Φ1 is the total flux linkage, and this is due to current I1. So N1 is 500 multiplied by 0.6, that is Φ1 you have calculated, divided by 5. So this is in milliweber. So therefore you will get the answer in millihenries, 60 millihenries. Similarly, mutual inductance. So mutual inductance is given by the formula. So the N2 into Φ12 by I1. So this is the formula. So that is the number of turns in the second coil multiplied by the flux linkages in that coil due to the current in the neighboring coil. Therefore, that is 1500 into 0.4 by 5, which will be equal to 120 millihenry. Then find K. K is nothing but the flux linking with the neighboring coil to the total flux. Φ12 by Φ1, which will be 0.667. Then using this formula, M is equal to K into under root of L1 into L2. So M is known, K is known, and L1 is known, L2 is unknown. So you can find L2 as 540 millihenry. Coming to the next problem, obtain the equivalent inductance of the parallel connected coupled coils shown in figure below. Assume K is equal to 0.7, given L1 equal to 0.3 henries and L2 equal to 0.8 henries. So L1, L2 value is given, and the coefficient of coupling is given as 0.7. Now you are asked to find the equivalent inductance. So here the mutual inductance K is given by K into under root of L1 into L2. So K is given and L1 and L2 values are given, substitute. So you will get 0.342 henries. Also we know that for this circuit, so current I1 and I2 are entering the dotted terminals. So the equivalent inductance of this circuit will be L1 into L2 minus M square by L1 plus L2 minus 2M. So this already we have seen in the coupled circuit part 1 video. So now you substitute L1, L2 and M equation. So you'll get L equivalent as 0.295 Henry. So if you want to find out the reactance, equivalent reactance is nothing but V by I. So this is nothing but J omega into L equivalent. L equivalent you know, so you can write it as J omega into 0.295 volts. So this is the equation for the equivalent reactance of the circuit. Next problem. Two coupled coils have self-inductances L1 equal to 50 millihenry and L2 equal to 200 millihenry, and a coefficient of coupling K is equal to 0.5. If coil 2 has 1000 turns and I1 is 5 sin 400t ampere, find the voltage at coil 2 and flux. I think you have understood this problem. So there are two coupled coils. The self-inductances are given. Coefficient of coupling is also given. And the number of turns in coil 2 is given. And the current flowing in the coil is given as I1 equal to 5 sin 400t. Current is given time domain. So find the voltage at coil 2 and flux Phi1. So Phi1 is nothing but the total flux produced by coil 1. So now let us see the solution for this problem. M is equal to K into under root of L1 into L2. So in this, K is known, L1 is known, L2 is known, so you can find out the mutual inductance. So once you know the mutual inductance, already we have seen that the voltage induced in the neighboring coil will be equal to, so mutual inductance times rate of change of current in coil 1, M into di1 by dt. So now I1 is given. So now you differentiate this with respect to multiply with 0.05, you will get 100 cos 400t volts. This is the equation for voltage induced in this coil 2. So now if you are going to assume that the magnetic circuit is linear, then we can write the following equations. We can write mutual inductance as N2 into Phi12 by Phi1. Also this can be written as N2 into the Phi12 can be written as K into Phi1, that divided by I1. So from this you can find Phi1. So Phi1 will be equal to, so M into I1 will come to the numerator, and in the denominator you will have N2 into K. So now you substitute the values. So I1 is 5 sin 400t. So you substitute M and N2 and K. So this you will get it as 5 into 10 to the power minus 4 sin 400t. Hope in this video you have learnt about how to find the equivalent inductance of series and parallel coupled circuits, then how to write KVL equations and find the mesh currents and power supplied by the source, then how to calculate self and mutual inductance from the given data. Thank you so much.